Welcome back, everyone. Our next event is a startup panel, and that will be moderated by Pranav Gokhale, who's the founder of a recent quantum startup called Super.tech. And today, Super.tech joined the Chicago Quantum Exchange, so it's a pretty exciting day. I'll welcome Pranav, and he'll introduce the panel.
Thanks, Dana. It's a pleasure to be with you all in this virtual environment. And as a founder of a very recent quantum startup, you can imagine that this panel is of personal interest to myself because a lot of the startups that we're going to hear from today, the three startups, are sort of examples of where I want our own company to go. So I'm on a personal level really looking forward to hearing from their insights and their perspectives and their takes. So we've got three startups today and executives from them. And so I'm going to go ahead and turn it over to each of them to give a quick introduction of yourself and your company. And maybe the best way to frame this is, how would you describe your path and your company at a dinner party, at least pre or post-COVID? And let's go alphabetical by the startup name to disambiguate the two Christophers. So let's start with Chris Monroe from IonQ. So if we can hear from you for 2 or 3 minutes on your background and how you describe IonQ at a dinner party, that would be fantastic.
Sure, thanks. I'm Chris Monroe. I'm a co-founder and chief scientist at IonQ. We're located just inside the Washington Beltway in College Park, Maryland, just off the campus of the University of Maryland, where I've been for the last over a decade working with individual atomic qubits based on trapped ions. And my co-founder, Jung Sang Kim, and I sort of met about 15 years ago and started systematizing this very exotic technology of individual atoms levitated on a chip in a vacuum chamber controlled with laser beams, and realized the vast potential for this for flexible, reconfigurable, fully connected, scalable quantum computing. So a lot of big words in there. But the beauty of the atomic qubit is that it's perfect when idle. Because it's based on atomic clocks. Each qubit is an atomic clock, so they're perfectly replicable. And all of the challenges going forward to scale up is really on the engineering side. We don't need any breakthroughs in quantum physics to realize this. Sorry, my camera's moving around. We don't need any breakthroughs in quantum physics for this technology to hit pay dirt. And we do need a healthy dose of engineering, and that's the challenge in the field, to get engineering to leave the universities and go into the industrial world, where engineering and making reliable systems is really the name of the game there. So if I were at a cocktail party, I mean, quantum physics is wonderful at cocktail parties because nobody understands it. Nobody has a kind of a feel for its basic tenets, because we don't have any familiarity with the idea of superposition of things in multiple places. So sorry about my camera. So what I would explain with these atomic qubits that we use is that we can create arbitrary entangled superpositions with near perfect measurements. They really look like laboratory systems, but at IonQ and a few other companies throughout the world, we're starting to engineer these systems to build some of the most powerful quantum computers out there. And again, I think our calling card is that we haven't even played near our final hand. We know exactly the technologies that we're going to be integrating ahead to hit very large scale quantum computing systems. Thank you.
Fantastic. This is an exciting cocktail party, so let me know when it's going on. So the next panelist is Jennifer Elliott, who is from Keynet, and same floor is yours.
Yeah, hi there. My name is Jennifer. I'm one of the co-founders of Keynet. So we're actually a Canadian-based startup, and we're working on satellite-based quantum key distribution, or QKD. We are a spin-out of technology developed at the University of Waterloo in Canada. And I think you're right, this is not your average cocktail party. I'm going to assume some of you are familiar with QKD. But at a high level, it's a way to exchange secure encryption keys from point A to point B. There are different ways to do this, but one of the most common ones is to send individual polarized photons, where each photon is a bit of the encryption key, and it's enabled to send very secure encryption keys from point A to point B. There are certain limitations to doing this on the ground, and so doing it via satellite enables global distribution. Yeah, and so I guess my background is that I'm an aerospace engineer, so I kind of have a unique background, but Keynet is also a space-related startup, so that's why I'm here, and I do business development and sales for Keynet.
Great. And then finally, we've got Christopher Savoie from Zapata. So close us off.
Great. Thank you for having me. First of all, happy Friday the 13th in 2020 to everyone, which is pretty scary, and maybe explain some of the laptop classical physics that were happening with Chris over there. Who knows? Maybe just a coincidence. My background is in molecular biophysics and molecular simulation, a field that probably will have where quantum computing will probably have some significant impact over the coming years. And then later in machine learning, classical machine learning, through which I met my co-founder at Zapata, Alana Spiragushik, who everyone must know if they're in this field. The 6 degrees from someone in this field. I think it's like Alana is like 1 degree from everybody in some way, shape, or form. And basically, I have been involved with Alana in another startup applying machine learning to classical machine learning to quantum chemistry. And now he had to spin out the software that had been coming out of his lab to apply to quantum computing, which is what we do. So we're the cocktail party, I guess, elevator pitches that we're an enterprise software company for quantum and classical computing. So Gokhale and I and 4 of his colleagues at Harvard spun the company out at the end of 2017 to really bring software into this space. There are a bunch of hardware companies starting to work on these qubits. It was starting to get real, but there wasn't a lot of high-level software to deal with industrial level problems in this space. You know, we have Python tools that are out there, a bunch of different frameworks, but we really didn't have any industrial level tools to handle the kind of workflows that we need to do if we're going to do this at scale. You can do things in a Jupyter notebook on your laptop if you're doing small simulations or working with 5 qubits on the cloud. But when you want to do 30, 40, 50 qubit experiments, either on a real machine or on a simulator, you need some real serious compute. And it's a lot of the other stuff that goes into doing an industrial enterprise solution that really hasn't been a focus yet in the community. And much like Chris said, you know, the engineering has to happen, and that includes software engineering. A lot of that had not happened yet. And so we've created Zapata to really attack the software engineering problems. And a lot of them are not sexy problems. They're stuff like ETL and, you know, data management and data loading and data post-processing and this kind of thing. And you have to do all of that to use these near-term quantum computers at scale. And that's what we do.
Great, thanks. So just to give an overview, I'm going to speak with our panelists for 30, 40 minutes, then leave 10, 15 minutes at the end in case there are audience questions, and I see some are bubbling in the chat, so we'll be sure to get back to some of those at the end. But I want to start with going in reverse order, let's say, because Christopher Savoie has touched on this a little bit in terms of applications. Where is quantum going, and where is your company going in relation to that, let's say in the next 5 years? And why is it important to start working on quantum today, even when we know that the real gold mine is going to be years down the road? Maybe you can comment on how many years too. But let's go in reverse order, starting with Christopher Savoie, who's touched on a little bit of this already.
Sure, yeah. I think why start now? Well, if some of us who've been in enterprise software before, I ran enterprise architecture at a 48 company before, and was there when data science really started to hit home for a lot of these companies. And we were kind of late to the party because we were in the automotive industry. And if you don't start now, you're never going to be able to really catch up in the infrastructure sense and in the workforce development sense, and having people who know how to use this stuff. It's not as though you could show up tomorrow with a million qubit, fault tolerant, beautiful machine that does perfect quantum computing, drop it into your infrastructure, whether that be in the cloud or in your data center, and start quantum computing. Big data never worked that way. Really, you need to get all your other systems in place. And enterprise data is really messy. A lot of 90% of a data science job is usually data cleaning and getting the data right before you do anything in classical or quantum machine learning. That's going to be the case. So getting that infrastructure in place, getting those tools in place, and getting that workforce in place before, in whatever time frame that computer shows up, is critical to actually be able to make use of it. So there's that reason to start. And I would add one other thing, which is IP. So the folks who get started now are going to, in their areas of domain expertise, have potentially blocking IP compared to competitors for all of these things, like chemistry, like optimization, like machine learning. And if they have a patent that lasts 20 years and 5 years from now that computer shows up, or 7 years from now, they've still got 13 years of blocking you. And you may need a license, so this could get quite expensive.
Right. And Jennifer, how about from your perspective, working in the security and quantum networking space?
Yeah, no, definitely. So I think my answer is going to be a little bit different from the Chris's, because I have, we're working in a different area related to QKD and cybersecurity. So kind of the motivation for QKD is that current encryption algorithms have a recognized vulnerability to quantum computers. And it's possible that some of the encrypted information that we currently send back and forth could be downloaded and stored so that it could be broken in the future by quantum computers. And so with this kind of, I guess you'd call it like a download and wait attack, it's possible for bad actors to obtain valuable information. So that could be IP or other kinds of valuable information that's valuable into the future. So for, I guess, cybersecurity specifically, it's really urgent that we do something, I'd say not only now, but probably a few years ago, because, updating our networks, updating our security takes time. And, while that time is passing, people could be downloading our data and using it in the future. So then I guess the other thing I'd say, so QKD is one of the things you could use to, have encryption keys that are secure against attack by quantum computers. But there also are post-quantum encryption algorithms that are used as well. So I think that's why it's really important to be used today, and it is being, both of these technologies are being implemented today, especially post-quantum encryption algorithms. As far as where it's going, I guess at conferences I notice that the crowds are getting larger year by year. So QKD is a growing industry. When I speak to some of my colleagues who've been in the industry for over a decade, they say, initially it was very academic. There was not a lot of commercial interest, but now we are seeing commercial interest. So I think that will just continue in the next 5 years. There are QKD systems commercially available, and I think they will be much more widely commercially available in 5 years, I should say.
Right. Your point about retroactive decryption should keep a lot of people up at night, I think. It's just the diplomatic disasters that would happen if all of our cables were leaked in 20 years even. That would be pretty bad. So finally, yeah, Chris Monroe, let's hear from the hardware trapped ion perspective. Where is your technology going in the next 5 years? How does IonQ going to help shape that path?
Well, you got a couple of great responses already, especially on the security side. I mean, the timescales, we're talking about political timescales that are of interest here when it comes to data security. So The time scales being so long, you really have to stay ahead of the curve. But I might get much higher level and sort of compare to the era when digital computing first started in the 1940s. There were these differential, these difference engines that were analog machines. Digital computing, started by Claude Shannon and Alan Turing, totally different approach to computing and even ascribing information. And it took, it took a culture, a new culture of scientists and engineers to embrace it, to realize that it's much more stable. And that was a very late thing that happened in the 50s. Now, quantum computing is even more different than both analog and digital classical computing, of course, because of these fundamental, tenets that come out at cocktail parties that's so fun. But there is a cultural divide on what it means to store information, what quantum information means. We have no idea really what the killer apps are. We have some great hints, but why do you need to get in early? As a hardware player, there's a huge thirst for running algorithms on real machines with real errors. And so at IonQ, we're not just building hardware. In fact, almost half our company is on the software side and controller side. And we work with our friends Chris and Ellen at Zapata and other companies that have some interesting takes on particular algorithms, how to compile them. But Chris, this will sound familiar to you, but we're constantly working on people on the algorithm side to dig down deep into our own hardware, because all hardwares are a little different and they're not yet a commodity. So it's very hard to write successful quantum software that is hardware agnostic. I think in 20 years we'll be there, sort of like the way we are with classical computing. I think of the cell phone pictures that we take. They're 10 megabytes. You don't need that resolution, but memory is cheap. It's a commodity. And when qubits and quantum circuits are a commodity, reconfigurable and all that, then I think the software is just going to totally take off. And I think IonQ will eventually be a software company. That's in our particular technology. What we like to do in our roadmap is to move everything we can up the stack to software, to the controller and to the software. So we don't have any wires in our qubits, for instance. They're wired from software through optical beams and so forth, and very well engineered controllers. And so that's a totally different way of thinking about computing. And our roadmaps, we think 5-10 years down the line what we'll be doing. It's not exactly clear, but we have a very concrete technical roadmap, and we're going to need some time and investment to get there.
Right. And I think all three of you have done a great job of spelling out what exactly makes quantum technology so different from classical and previous technologies. And then I think there's, sort of switching gears here, there's another thing that's different from sort of a geopolitical economic perspective, which is how diffuse quantum is across the nation, across the world. And maybe this panel is a good example. All three of your companies are headquartered in very different places. And so the question that I want to get at here is there's folks who are policymakers, university officials, research institute officials in this audience. And what is your message to them about what can be done to bring the quantum economy to a particular city like Chicago or to any other university? What needs to be done with policymakers, with research institutions? How do we make quantum happen in a particular place? And this can be an open floor question.
Yeah, I might start quickly, I guess, because I'm here in Washington. I sort of got pulled in to a lot of policy discussions that predated the National Quantum Initiative. And the argument that carried a lot of weight, it always does and it still does, is the fact that, this is very simply put, but universities don't make things. Universities do great research, and at the same time, universities are very familiar with quantum physics, quantum mechanics in our science and engineering colleges. We teach students this. It's sort of common currency, but we don't build things. I would never get in a helicopter that was built by a bunch of graduate students. That systems engineering is a very complex subject that is not really taught. You have to do it for decades to really get into it. And so there's the divide, because industry is almost complementary. That's where the systems engineers are. But up until 5 or 8 years ago, industry largely didn't have a familiarity with these weird fundamental tenets, maybe at cocktail parties, but that's it. I mean, there's a reason they're drinking booze while talking about this stuff, because some of them, frankly, don't even believe it. They're the strange laws. So what I've argued downtown very effectively is that this is the role governments can really play, especially in the U.S., our national laboratory systems, Department of Energy, NIST, the Department of Defense, National Science Foundation doesn't have laboratories, but they fund this field in a big way. But the institutes, especially DOE and NIST and DOD laboratories, this is where people know quantum, but they also build things. So it's that nice intermediary between the universities and the private sector, and they can play a big role in ushering this technology and the use of quantum computers and quantum technology over to industry. So we're seeing this in many other countries. Europe and China in particular are taking very centralized approaches. They're used to, I think the US, we don't typically have such a centralized version there, but we have many different agencies that have different missions, and they're all playing a big role. I mean, it started with defense and intelligence 25 years ago, and they continue to really push this field forward. But I think more recently, the DOE laboratory system, which is really the pride and joy of our science here in the US, they're starting to play a huge role. And of course, Chicagoland is home to two very visible laboratories in that area.
I could go next if you'd like.
Sure. I think okay. Christopher Savoie, your microphone might be muted, just FYI, but let's go ahead with Jennifer.
Okay. Sorry, I actually missed the last thing you said, but so I guess I might have a little bit of a different view to Chris Monroe. I think, to me, it seems like quantum is at such an early stage that you kind of do need a proximity to universities. So, you have government funding into research in the universities that brings in grad students that exchange ideas and academics that collaborate. And out of that, you have some interesting stuff born. And you can see that in Canada anyway at the University of Waterloo, the Institute for Quantum Computing. And then what has happened there anyway, so I have one example, is companies spin out of that and they tend to stay in the area. And so now there's basically, we call it Quantum Valley in Waterloo. So yeah, I guess my thought is just that quantum technology is early enough that having a proximity to universities is still necessary. Although I completely agree that building real stuff that works and having people with experience that do that, and also people who have experience, getting stuff to market, is something that universities don't do. So, I don't 100% know the answer to that question, but that definitely is a challenge. But anyway, proximity to universities initially, I think, is my thought.
Is my mic working? Is my mic working?
Yeah.
No? Okay.
It is working.
Yes, it is.
Okay, good. Yeah, so I guess I would say that there are kind of two concentric things here for a startup, just in general, right? Is money, and money matters, right? And so that money has been concentrated into certain metropolitan areas in the U.S. as far as startup money goes, and therefore a lot of the the executive teams who know how to take a startup and grow it, and the venture capitalists who know how to take a company out of a university and grow it, are in certain regions. And it's really hard when you have to pitch 20 venture capitalists to get one to bite for a startup to not be in a region where there's some concentricity of that. So for executive talent and venture capital. So I think there's still, if you look across here, there's a little bit of diversity there. But, Silicon Valley, Boston area, Northern Virginia, DC area are kind of the tech hubs. Chicago as well has money, but I don't think by anyone's estimates is in the same category as Silicon Valley, Boston, Northern Virginia, as tech hubs. So that exists. However, one of the other problems that we have in this particular industry, and it's an acute problem, is that you have to be able to recruit quantum scientists with some quantum computing capability in our field. Even in the quantum sensing field, I would imagine there aren't thousands or millions of developers. So it's not like you just hang up a shingle in Silicon Valley and you have all your people there who know how to do this. Our field is a much smaller field of expertise, and the scientists and engineers who know how to do something in this field are spread throughout the globe. That's a reality that we have. We're fortunate in some sense that we're not experimentalists. We are a software company, so we've been able to hire, even though we are based in Boston in one of these tech hubs. 1/3 of our scientists and engineers are in Toronto, for example. And one of our best programmers is in the Congo in Africa and works virtually. We have to do that because the talent here is global, and particularly this coronavirus has made it more acute that we have to take people where they are, literally, geographically, and be able to utilize them. And in a software company, we're able to do that, fortunately. So we're very much global in our footprint as far as where we're doing our science and our technology development. But the concentration of capital, I don't know. I don't see that particular part of the equation and executive talent geographically that's going to change terribly much over the coming years. It's really hard to become a Silicon Valley or a Boston area or Northern Virginia overnight. To be that at least is my opinion. It's there's so much infrastructure. You need generations of the talent of how to take a company and exit a company for investors. For that to become really a gravitational center. There will be exceptions. There always are. Not every technology company in the world is in one of those centers. And I forgot the Seattle area in software, and that's an important one as well. But those are exceptions. Those are outliers.
Right. Very well said. So I think that sort of gives a good sense for the quantum industry as a whole. And I next want to talk about your individual startup experiences and echo one of the audience questions from Felix Liu, which is, what have been the main surprises in your startup journey? Have things gone and played out as you expected? What has been the main deviations? And you can feel free to take this in any order.
Yeah, I mean, I can take this.
Go ahead.
Yeah, so I guess, I don't know if this should have been a surprise, but just when you're developing hardware, how long it takes. So that's been sort of a surprise, although, probably should have been anticipated. And I guess the other thing too is, at the moment anyway, how kind of collaborative and collegial the quantum industry is. As was mentioned before, it's a very small industry. And I will often see companies that are, potential rivals or potential future rivals collaborating, which you definitely don't see everywhere. So that's, I guess, been a nice surprise. Part of that might be because the quantum industry is still quite linked to academia, and academics are used to collaborating. So that might change as, the industry commercializes more. But yeah, I think those are a couple of the surprises that I've experienced.
Echo the camaraderie and the friendliness between what in other industries might have been potential rivals. I see that some myself.
Yeah, it's a great thing about this field. I don't really think we're at the point where there's a zero-sum game anywhere. So what's good for the behemoths, I think they bring very much interest to the field, and it affects all of us, even the small startups. So to your question about surprise, I guess the main one will end up being speed. But when I hadn't really thought about forming a startup very seriously, or anyway, at all. And when I started collaborating with, again, Jungsang Kim, who's a professor at Duke University, I was at Maryland. I'm now moving to Duke, by the way. but I was approached by a venture capitalist in my academic office in 2014. And this fellow, he's a real high roller. Later learned he's really one of the highest flying venture capitalists on the East Coast. Works for New Enterprise Associates. And he came in my office and he was waving a paper that Jungsang Kim and I had written about a modular architecture to scale up trapped ion quantum computers. It was published in Physical Review A. And so this VC comes into my office. He says, I read this paper. It reads like a business plan. And so he was a nice guy. I liked talking to him. So we ended up meeting every few months for about a year. He said, are you ready to roll it out? And I brought Jungsang into the equation, and we sort of put him off for a while, thinking that, we're not ready for this, maybe in 5 years or something. And then in 2016, in one of our projects, where we were making entangling gates and so forth, I'm an atomic physicist. I spent most of my life inside of a laser, lining up optics and so forth, like what a good atomic physicist would do in the lab. But in 2016, we built a system that once we calibrated it in the morning, a couple hours, it takes a while, all afternoon, we would not be doing atomic physics anymore. We would be running algorithms on a PC and actually running them. It was actually more like a real computer where the user doesn't need to know the guts of things. And it was very interesting. It was those few months were just incredible for me because we were learning about things like cosmology, information in black holes, quantum chemistry, that Chris knows so much about, other applications that I'd never learned before. And I guess the surprise was that was the year that IBM, made their systems available on the cloud. It was a 5-qubit system. Our system at the university was 5 qubits, coincidentally, but it knocked the pants off anything IBM could do because our performance was much better. Of course, IBM was on the cloud, so they were running 24/7 and they had great engineering. We had to calibrate in the morning and then run. So we started working with all kinds of collaborators, almost like a user facility. And then we started thinking, maybe the company thing is not a bad idea. So the surprise, I think, is just how fast that turned around. We thought it was 5 years away from starting a company. It turned out to be a year and a half. And then, IonQ now is about 70, 75 employees. And we built 5 systems. The next 3 are being designed and built right now. So we're just, it's just the speed of the field in the last few years. That's been a total surprise to me.
Yeah, I guess for me, I would echo Chris's comments there. That the surprise is that the pace and the accelerated pace of everything, the pace of investment by companies who are getting into this field, the level of investment by end user customers who want to get involved and don't want to be late to the party when these computers show up with advantage over classical systems. That has been surprising. The other surprise, I guess, is what's so unsurprising in some ways. That's in that, I've been through generations of deep technology before with the Siri story and my early involvement in that. And, people, when I was out selling the concept in, late 90s of, talking to your cell phone and getting an answer in natural language on your phone, people looked at me like I had 5 eyes. And I kind of felt that way about quantum computing when we were in the 2, 3, 4 qubit phase with really lower 2 qubit gate fidelities just a couple of years ago, actually. And that I guess is unsurprising in the sense that there's a development here that's happening like every other technology thing that I've seen. There are the pundits who are on the opposite side saying this will never work, that's crazy. And on the other side, you have the engineers who are just doing the work. And you have the early adopters who are out there investing in this ahead of the curve. And, it kind of is like deja vu all over again. It takes time. And there are going to be visionaries and curmudgeons out there. And I guess I'm on the optimist side, and I'm seeing it all over again. People thought I had 5 eyes back then saying that this is going to work. And I feel a little bit of that now in this industry. But I think hopefully that I'm going to be right again.
And I'm going to piggyback back off of one of your points, which is that essentially we're going to need a lot of more visionaries. And I'm seeing this in the audience questions too, a question about who's hiring the workforce. So let me broaden this into a question of, in the audience at this event, there's a lot of young undergraduate students, graduate students who are thinking about their careers in the next 10, 20 years. And I just asked you all to speak to your own company's anticipated workforce demand and what you might want students to start thinking about in terms of preparing themselves for a potential career in quantum technology.
Well, you don't have to be an expert in quantum physics to be in this field at all. I've always said that quantum physics is not hard. That's the wrong word. You know, calculating the Navier-Stokes equation for turbulence in a fluid, that's equally hard. In fact, you could argue it's even harder because it's highly nonlinear. The quantum wave equation is linear. It's actually not hard to apply its rules. What is different about quantum is that it's different. We don't have analogies in everyday life, as I said at the outset. And those are easy. It's easy to learn the prescriptions to quantum. It's in fact trivial. You can learn them in a half hour, really. I think students tend to shy away from the field because they think it's a little bit too egg-headed. But this is a new way of storing information. I think we're seeing lots of computer science students, even on campus at the University of Maryland, just a half mile away. I have a couple of students from the electrical computer engineering department and computer science. They're interested in this field, and I take them willingly. I love having them in the group, and I think computer science departments are they're exploding at schools like Maryland and also at Duke, and we're getting more and more interest at the university level. So I didn't mean earlier to poo-poo universities in this field. We absolutely need them. They're the ones that will train our future people in exposing them to quantum computing. Yeah, I don't know. I find that it's largely happening already, and it's largely owed to big companies like IBM and Google really making a presence in this field. They're getting out there. They're outward looking, and this is great for everybody.
And let me add, Kristen. I'll just make one comment which Chris might be interested in. So I myself grew up in Maryland, near NIST and the University of Maryland. I got to intern at NIST in high school, and it's very much because of the work that you and other JQI folks were doing to do outreach and things like that. So I'm a sort of product of the workforce development that you've planted seeds for since the 90s. But let's go ahead to Jennifer.
Yeah, sure. So basically, I was going to agree with a lot of the things that Chris said. So Keynet is smaller than the two other companies, and we've been hiring junior people, and very often they just have transferable technical skills, and we've been training them, and that's worked well for us. So maybe my, advice to undergrads would be, make sure you have transferable technical skills if this is something that you're interested in. And I think that as people see a market emerging and see jobs emerging, there will be more students will, choose to pursue graduate studies in quantum because they'll see that there are jobs for them, doing what they learned and what they researched. So I think that'll kind of happen naturally, and I think we're already seeing it a little bit for sure. Yeah. So I guess I would just say that. I guess one thing is, I think probably, we rely on our co-founder team to have technical leadership. And I think once we need to hire externally for technical leadership, for people who have very specific skills, that's going to be harder. I'm worried about that.
Right.
I think for me, the answers are very similar. I think on the software side, I echo Chris's comments in saying that a strong computer science background, I think, is a good place to start because the quantum pieces of this are linear algebra. Hopefully, a computer scientist has had at least some mathematics on the linear algebra side that is, I would say, easily attainable, if not easily transferable from there. The hardest thing is taking a problem and reformulating it with a new algorithm that works in a quantum way. So that on the software side is important. I'd say there's another part of it as well, and I think it was alluded to in Chris's previous comments as well, is that being agnostic in hardware, at least for the foreseeable future, is not really an option. So on the other side of it, we do need people who have good capabilities in sending pulses by a laser or by electricity, electromagnetic fields into these devices, and understanding those and interpreting those. And so that engineering side of things, the electrical engineering aspect of this, if you will, RF, these kind of things are also really important. And the quantum part of that, again, I think is learnable if you're a very good engineer or experimental physicist. It's transferable into quantum computing. So I think both of those aspects are important. Just a note, though, one thing that we really want to see happen, and maybe it leads to a different part of the discussion, but this is really a hard field to find, particularly gender and ethnic diversity in. To a great extent, and racial diversity. This is something that we have to do a better job at. I think earlier in the pipeline, and we're involved with the U.S. government in some initiatives, the Q through 12 initiative, and other areas to try and improve this, but it takes time to build that pipeline. We've been pretty fortunate with some of our diversity at Zapata, but it's really hard. It's really hard, especially at the senior levels of science, where you're trying to combine two fields, computer science and physics, where particularly on the gender diversity side are already difficult areas, and you have that concentric Venn diagram in the middle, and it gets even harder. And I think we just really, as a workforce, diversity. From that angle, we really have to do a better job, and universities, I think, can play a great role in doing that and encouraging women and minorities to go into this field for us. And I think that has to happen at a deeper level. We can do well on the demand side by helping as companies, but we really need that pipeline filled out better on the university side to do to accomplish our goals in diversifying our workforce.
I'm very glad you brought that up. Actually, I'd love to hear also from IonQ and Keynet as to what your company is doing and can be doing, and the industry can be doing in support of diversity and inclusion.
Yeah, I mean, I can start. I think it is a hard question to answer. It's one of those things that takes time. Since like my undergraduate days, I guess, in engineering, there's been discussion of how do we get more women and minorities into engineering and sciences. And I think, my perspective is to see, people want to see people like you in leadership roles. But again, that takes time. I agree with Chris that universities can do a lot to encourage diversity, with having targeted scholarships, for instance. And then, yeah, again, I don't think there's a great answer to this other than that companies need to be mindful that, diversity is important, and it helps the company themselves, and think about ways that they can improve the diversity of their company, and just, acknowledge that it's probably going to be a slow process.
I guess I'll be a little more passive. I was just thinking for the last 30 seconds that my first graduate student, she's now the head of the hardware lead at Honeywell. At the university, I've had a big group historically for the last 20, 25 years, typically 15 grad students, 5 or 6 postdocs, a few research scientists. And, I don't stop to think about it that much, but maybe it's a quarter to a third have been women. I don't know, it sort of happens that way. I think Maryland is such a huge influence with JQI, the Quantum Computer Science Center. NIST as an entire agency is bought into this field as well. So we it's not at IonQ that we only take Maryland people, but being in the middle of this big ecosystem really makes it easy to tap into almost anything we want here. So at IonQ, I don't know exactly what the numbers are, but they're not bad at all. I think they're overrepresented compared to what you might see in a typical physics or computer science department. But I don't disagree with anything that's been said. We want people, every type of person, no matter what, coming into this field.
So I want to switch gears now and ask you all, what keeps you up at night when you're building your company? And what do you perceive as the biggest risks to quantum and to the industry and your company, and what could be done to mitigate these risks? And maybe we can start with Jennifer. Or
yeah,
go ahead, Chris.
Sure. Okay. Yeah. No, that's a really good question. There are a lot of things that keep me up at night. So I think for Keynet specifically, but this would I think go for any kind of quantum hardware company. So for us, when you're dealing with both space hardware and quantum hardware, there are both large capital costs and long development times. So if I were to look at a your typical software startup, they can very quickly develop their minimum viable product and test it in the market with very little cost, and we just don't have that luxury, unfortunately. So we have to start out with dealing with these long timelines and these large capital costs, addressing a market that we have some uncertainty about. And so, that's high risk. And that's just kind of, I think, the name of this game right now. I think that's pretty much it.
I guess I lose sleep over the uncertainty in the field. On the hardware side, I actually don't lose sleep over our technical progress. We're gonna miss some milestones. We're gonna hit some early. I don't worry about that. That's sort of short-term stuff. I worry in a sense that in 10 years, that if somehow the private sector doesn't come up with an application that's useful for business, that's huge. But I can't say I entirely lose sleep over that, because I also know, this will sound overhyped, but it's true. There are certain problems out there that will never ever be solved outside of quantum computing. That doesn't mean a quantum computer will actually solve it, like a traveling salesman problem. But problems that combinatoric optimization problems that have more configurations than there are electrons in the universe, you cannot tackle those problems without quantum computers. So this topic will be around, whether or not there's an advantageous algorithm that everybody wants to use next year or the next 5 years. The search will continue, and it sort of underlies why we need to have not just industry, but government laboratories, national labs, to maybe keep the inertia going for industry to take off in the long run, and of course universities keeping spinning up things. So I guess it's the uncertainty of it all that makes it a little strange. Usually in business, you have a business plan to a product, and you have revenue streams, and you can kind of count on this. Of course, you have to compete with others. But in quantum computing, we don't have to compete with regular computing in a way, because there are certain problems out there they will never be able to touch. So that allows me to sleep better at night. But the uncertainty is a little unwieldy.
And luckily, quantum physics is probably, quantum physicists are the best people at dealing with uncertainty, so you've got an advantage there.
I guess,
Chris Savoie?
I guess for
we're okay with
for me, I think my biggest concern really is the hype itself, and I think I guess to be more specific, it's setting expectations to investors and the general public as to the timescales that we're going to have to deliver some actual advantage and business value. I believe that that'll happen. I believe it'll happen in a time frame that still does make sense commercially. But I've been, kind of been here before, with the whole voice-based systems and the whole Siri thing. And, starting in 1998, really, that wasn't productized until 10 years later. It took 10 years. And so setting realistic timeframes for investors so that there isn't what do you call it, a quantum winner or whatnot, I think is vital to us all. And I guess our joint enemy is the hype in some ways. We have to be realistic about the timeframes that this stuff takes to do. I mean, we're doing some really difficult engineering here, and the payoff is going to be huge. I think everyone agrees, or there wouldn't be any investors in the space. But the timeframes it takes to actually deliver advantage are longer term than just creating some little mobile app and hawking it to Google for an exit. So I think it's careful. It behooves us to be careful about what expectations we set scientifically and business-wise to the community. It really behooves us to set the right expectations. And if you're an entrepreneur, I would say set the right expectations with your investors and choose your investors carefully. I think we're very fortunate at our company to be dealing with some sophisticated investors who are very deep tech oriented, who know this is going to take time and who are patient and who aren't expecting a quick flip or a quick IPO in the next year or two. And that's really important. And I think that there is a risk that, people seeing the amount of money that's flowing into this space because of the eventual scale of the payout that we all know is going to happen, that they may be fooled into thinking that payoff is going to happen nearer term in the next couple of years. No, we're in this for the long haul. And I think the investors who are here need to be in it for the long haul. And it is very much the responsibility of the scientists among us to give people realistic expectations of when that's happening and have real integrity scientifically and business-wise in how they communicate to others the realistic timeframes of when this is all going to start to become something that has those huge venture returns for people, which will happen, but it will take time.
Absolutely. And this is a good transition to the top audience question right now, which is, if you would care to speculate, with this in mind about making sure that we have realistic expectations, where do you see the most commercial activity, Cameron asks, for quantum computing in the near-term era, or when it comes to Jennifer, to QKD in the near term? Which industries are we seeing potential in? And maybe we can start with Christopher Savoie, since this connects to what you were saying.
Sure. I would hate to limit ourselves to a discussion of verticals and what industry, because I think that's like saying what industry will computers help. So that's really, I think, not a really useful metric for us to look at. But I can say what categories of algorithms or things may have a nearer term traction. And we are coming to the conclusion that some of the nearer term advantages will be in quantum machine learning areas, quantum GANs, quantum machine learning techniques, QAMs, and things like this. And we'll be showing some pretty exciting results, hopefully, over the coming weeks and months in that area that really are early evidence to us in real experiments that there are going to be advantages in those areas. And some of those advantages are not just merely speed up advantages, although this is in a sense a speed up, but quality of model advantages. And we're seeing that in some of the literature that's out on the archive just in the last few months. So that's a trend that we are very much investing in, doing experiments in. And we will be showing some results pretty soon that we hope will be very exciting to people who are doing machine learning in real life, because that is an area that has already has classical implications in just about any industry that wants to have data-driven decision-making. And from R&D all the way through to commercial models within the industry's value chain in just about every vertical.
Right. Do we want any follow-up comments from IonQ from Chris Monroe?
Sure. I'll be brief, but very, very high level. We'll put my academic hat on for a minute. It seems to me that every quantum computing application takes advantage of, say, exponentially many configurations and somehow there's a forcing function that finds one output. So we're not talking about one-to-one functions here, but something that finds one answer depending on all those inputs. So I think almost every algorithm can be cast as an optimizer of some sort. So that's very vague. The thing about optimization is that it hits every sector of the economy, every one of them. Even electrons, they self-optimize how they're going to align themselves on the spine of a complex molecule, and it's up to us to model that with qubits in some cost function and find the ground state of that cost function. And then you can go to finance, you can the materials design, all kinds of different logistical problems. So it's it's a little bit of a vague answer, but because it's so broad, and like Chris says, what's the business case for using computers? This is like 1960, so I'm not too concerned about that. At IonQ, of course, we're just trying to build the best, most flexible, programmable, reconfigurable systems that have the largest gate depths and largest number of qubits. And I think working with places like Zapata and other small companies and other end-use customers, learning the structure of their algorithm, maybe we can co-design next generations of our hardware to better match with their particular problem. So it actually, as time goes on, it's going to be a very important part of our company. We can't afford to work one-on-one with 30 different types of algorithms. We have to pick and choose them, and we should do it wisely, because that is going to be where the first advantage happens. But all right, so I'm ducking the question. It's going to be some kind of optimizer.
Great. And finally, we'll have sort of orthogonal applications from Keynet in the QKD.
Yeah, so my answer is going to be different because QKD, is different. It's much more, I guess, specific. I think we understand the use cases much better than you would maybe with quantum computing. So I would say I think our initial users, or where it's going to be commercialized initially, is people who have valuable data and really care about their security. So I think that's going to be, government applications.
Right. Great. So we are reaching the end of our time, and I want to give each of you a chance to just say any closing thoughts. In particular, if you have a call to action, a website that you want undergraduate students, graduate students, policymakers, potential customers to be visiting, or any sort of last remarks that you want to make, if we want to go reverse alphabetical with Jennifer.
Yeah, sure. Well, thank you very much. This has been a great session. If you'd like to learn more about Keynet, you can go to our website. So it's spelled QEYnet.com. Yeah, I guess you could also, if you have a message for me, probably the easiest way is to reach out to me on LinkedIn. It's Jennifer Elliott, 2 L's, 2 T's on my last name. Thanks.
Oh, you know what? I got my reverse alphabetical wrong, so it's Chris Savoie next.
That's okay. That's fine.
Usually Q is later, but we're a Z, and we chose that intentionally so that we would get the reverse alphabetical order. I'm on Twitter at CJ Savoie, Savoie. And if you want to learn more about our software products, go to Orchestra, that's spelled with a Q, the Portuguese spelling of orchestra. And orchestra.io is where you can find us, and you can learn how to actually use that platform to interact with all kinds of cool machines, including the IonQ machine.
Great.
So very quickly, our website is ionq.com, C-O-M. If you're an electrical engineer, no background in quantum, we love to hear from you. Software engineer, of course, same thing. And if you're a student interested in physics or chemistry on the quantum side of things, IonQ has a very cozy relationship with both the University of Maryland, College Park, and Duke University. And we're sort of a family in a way. With Jungsang Kim, we've been doing research at the university level for 10 or 12 years that basically was the precursor to IonQ, and that relationship continues. So if you're on the younger side and you're in graduate school, please give me a call at my Maryland or IonQ address or Duke address. Thanks.
And just in service of one last audience question, raise your hand if you're hiring. or hiring-ish? Okay, great. And I'm sure there's broader industry opportunities for students out there as well. So I'd like to thank all of our panelists. We'll give a virtual round of applause. And I'm going to turn it back over to David Ashlam to close out today's session and the event.
Thanks very much, Pranav, and thanks to all of our panel members today. You know, we've had 3 packed days hearing about federal plans and activities in our various industries, learning about the new U.S. National Quantum Information Science Research Centers, exploiting opportunities for growing quantum science and tech here in the state of Illinois, and thoughts today about developing a new quantum economy. This week's summit's broken all of our records, actually, for participation in any quantum event, with over 1,000 distinct viewers from 42 countries around the world. So thank all of you for tuning in. I'd like to take a special moment to thank the governor of the state of Illinois for his enthusiastic participation in our meeting this week, the leaders of our U.S. federal agencies that spoke about their programs, the directors of the new U.S. quantum centers across the country, thanks for sharing with us, and of course our business leaders that have talked about helping to launch a quantum economy. And finally, I want to thank all of you for participating and give a special thanks to Kate Timmerman, the executive director of the Chicago Quantum Exchange, who led the planning and the coordination of this massive event and made it work so well. Thank you very much, everybody. Stay well, and hopefully we'll see you next year in person. Thanks again.